Good. Finally ready. Sorry for the slight delay. We're done with the actual content of the module, and given that the first of the exams are day after tomorrow, that's also in good time, I guess. What I thought is also useful, some of the results I've shown you during the last couple of weeks were at least not cutting edge new. They were somewhat old. Many were from the last 30 years, say, but also not all brand new. And as a kind of a contrast, here's some things that I left. I was tempted to update things. I'll show you some essentially identical presentation that I gave a year ago on a lovely conference called Fun with Algorithms. And this kind of a bit of a special conference. Let me maybe show you as well. It's only happening every even year, and they publish real papers with proper algorithmic theory, but that always have some. They always have some whimsical taste to it, or some non-completely, always with a wink of the eye somehow. For example, there was an attempt of how to do a balanced binary search tree with random coins from bottom up. And the whole talk was essentially how all these things don't work. Then there's hardness proofs of Super Mario games of various sorts. And I guess Eric Demain is a well-known name in some circles. Former child prodigy who was 21, prof at MIT. And he started this MIT hardness group, which is kind of a regular contributor to this conference with all sorts of hardness proofs that are certainly with, I guess, too winky eyes sometimes. But the constructions are serious. So they take all sorts of games and show how you can embed a SAT formula in this. Same techniques as we've seen, but for somewhat more fun games sometimes. Where's that? Where's that? Oh, right, the chair Pilates. Yeah, that was also serious. One of the organizers, was she, chair? Yeah, Tamir. She's super keen on having people being a bit, I guess, getting fresh oxygen into the air. And so after all the sessions, she was serious about this and kind of, in her very friendly way, pushy, so people would participate and put up some 5-minute videos and do chair Pilates. She claims she's also doing this in all her lectures. I was tempted to try it for the 5-minute break. I think I mentioned this in Efficient Algorithms, but then I didn't have the balls to pull it through, I guess. Also, the room is not exactly great for that. There was another fun one, which is hilarious enough in just the title. Yeah, a programming language embedded in Magic: The Gathering. That was also a phenomenal talk. So take everything that comes with a bit of the lens of this conference. Also, it's happening again next year. If some of the open problems in the talk or adjacent to it sound interesting, maybe we should go to some other island up Italy's coast and present it. And that's also why some of the formulations and the presentation are also a bit on, maybe on the extreme side. Maybe for a different conference, you would see very slightly turned down jokes. But I think this is a good way to approach algorithms. It's essentially still a hardcore theory question, and all the talks in the conference have hardcore theory proofs at the bottom of it. So that's a bit of a prelude. Let me show you a bit what the problem is. I started this digression with, I was tempted to update the presentation because there's some follow-up work on this. And so one part in particular, which I'm not going to tell you up front which one it is kind of outdated, or we know something much better about it. Maybe if we have time, I can sketch how that works at the end. And there's lots of loose ends that if someone enjoys this kind of puzzle and the kind of techniques that we've really looked at this semester can work there. So I think you'll recognize many things. All right. That's also left the old affiliation there, which is only old in that it's still a double affiliation. So it's not completely a lie. But I left everything frozen in time, if you like. Also, sorry for my voice. I spent some time in Liverpool. That didn't somehow help. Or it was the plane. One of the two. What is polyamorous scheduling? I give a bit of some introduction there. I should say the whole thing is the brainchild of my my former PhD student in Liverpool. And he would be able to speak a bit more authentically about it. But I'm doing my best, same as last year, where for unfortunate health reason he wasn't able to go to the fun conference, which I think he'll eternally feel unhappy about. Bit of introduction, then, as we do for algorithmic problems, what cannot be done, hardness proofs, what can we still do? Last chapter ties in well. And there's even a hardness of approximation proof in there. So the topic we had to cut out for time reasons on how to prove that problems cannot be approximated beyond a certain point, but only a very simple instance of it. And then some problem-specific thing, density, that I might have to sketch a few things on the side. Okay, so what's polyamory? If that's in the title, you have to explain it. The shortest definition is some form of having multiple partners, but the stress is that it's fully consensual. And apart from all the potentially emotional things that this entails, it seems to have a computational component that's nicely summarized in this tweet. If you want to regularly see certain people, and here the assumption will be you only see one person at a time. That's not always the case, but let's suppose. Then your days can become really short. All right. As a formal problem, we modeled this as follows. There's people. These are the vertices in a graph. And then there's pairwise relationships. Again, the assumption is there's only pairs or couples. No assumption that the graph is bipartite, so there's not necessarily fixed genders. It's just some undirected graph. But the edges are not all the same. Some relationships are more important than others. And so they have a growth rate by which the desire grows to see that person again every day that you don't see that person. So you should think of this as a function or a weight on the edges, function over time. So linearly over time, the desire grows to see a certain person again. And what's the goal of a good schedule for this? Now, we're assuming that this polycule is fixed. There's no more people coming and going, and there's no relationships falling apart and no new ones forming. Clearly a simplifying assumption, but fine, you have to start somewhere. And so we want to keep that going for as long as people want. So the abstract formulation is a perpetual schedule. So you want to have somehow, you would normally think of weekly schedules maybe for other tasks. It turns out fixing it to weeks is a bit, making the problem a bit too restricted. So instead, you keep perpetual schedule formally says you map all the days from now onwards to people you meet. And what can this be? So it's a subset of the edges that you schedule for each day, but it has to be a matching in the graph. The assumption is every person can attend to one other, can be in one meeting at a day. And so every day you have to pick some selection of people so that no two people are involved with two of their relationships. All right?
Can I ask a question?
Yes, of course.
We're trying to minimize the desire in the long term, right?
Yeah, I didn't say that yet. You could, in fact, at this point, I think there's different objectives that you could look at. In particular, you can say, I want to make people happy on average, or in the worst moment. And I might also look at the worst person, or maybe I'm trying to rather have, the sum of people's happiness maximized or something like this. There's many different variants, and some of them are a bit boring from a formal optimization problem perspective, but I think several of them make sense. Here we'll only look at one specific one, which is kind of, before we go through the example, is making this worst case point. So the worst person in the whole system and the worst point in time, that should be optimized. So it's kind of a mini max. We minimize the maximal desire ever felt, the maximal unhappiness. Is desire a negative thing? As a philosophical question. Here we say that's the pain of being separated. Okay? Here's some examples just to make the problem more clear. I don't think you need them, but the nice animations are there anyways. So we have the first day. The desire grows for all the couples, and then some of them can meet. And it has to be a matching, disjoint edges. And we'll record the schedule in this tables. On day 0, A and B and C and D met. And for the others, the desire stays at that level. Now the next day, so okay, these are happy now. But then the next day, by the same growth rate, it grows back. And for the others, we add another amount of the growth rate growth. Okay. Desire growth. Then on the next day, say these two meet. So that's just this edge. And you see, this is a maximal matching. You can't add any edges that doesn't involve A or C. All right. Then, because A and B didn't meet on this day, their desire grows further. So we can make them meet again. And now this one is growing urgent, so we schedule those. And from then on, you can repeat the same thing, and you see that this high watermark of heat is what we call the maximal desire ever felt. You see that this high watermark stayed the same over the second course. So initially 40, then we had to push it further, but then at 80 it could stay, and you can see that this is already the same again. So a schedule of length of a period of 4 is enough here to go around. Okay, is the problem clear? Now, this is maybe the first non-trivial mathematical thing to say. You can always assume that these schedules have a fixed finite period, so some amount of days, and after that, you just go round and round. Why is that the case? It's easier to see in what's coming up soon, but you can already here, you can see it's a discrete and finite system. You can schedule all of the possible matchings, but there's only finitely many. The graph is fixed and finite and given. So there's a certain amount of matchings that you can schedule in this graph. And all the possible states that you can be in, also for these desires, they'll just be integer multiples of the growth rates. There's not arbitrary real numbers that you can get. At any point in time, each of the edges will have a certain desire that's an integer multiple times its growth rate. And so essentially, if you want to have the heat bounded, any fixed heat, if there is a schedule, then there's a periodic one. Because if you restrict it, the whole system to stay below this high watermark, there's only finitely many places where it can be. So you can think of it as a large graph of all possible configurations. And every day can bring you from one configuration to another one. But if you're going to keep going this forever, infinitely, then in a finite graph, an infinite walk has to walk along a cycle. Okay, so there must be a cycle that you could have taken from in the first place, and it would have stayed below the same high water mark in the same way. So you can always, that's the first important thing, like we can even specify the output, right? Maybe previously this infinite schedule, how do you even output that as a program? But really it's enough to output this finite prefix, and then the infinite schedule is just repeating that. What I started with here is the optimization problem. So you're looking at, there's always going to be some solution, but maybe this heat is very high. And we can also go to a decision version. In, I guess, the natural way you would always do this, or we've always done this in the module. But here specifically, it's useful to spell out the precise meaning of what the decision problem looks like. If you fix a certain heat, right, so decision problem always has a threshold. The optimization, or the value we optimize is the heat here. So if you put a certain value here, you know exactly how often you can let each edge grow before it exceeds that threshold, right? That's these blue numbers. And we call that a frequency. So you just take the high water mark, divide by the growth rate, and you have to round up, because otherwise you're already over the bar. So the red numbers are the growth rates. The blue numbers are these frequencies. I hope the colors are distinguishable for everyone. I don't think I've always put decision or optimization there. Then I guess it's clear if this decision version has some solution where, say, this edge is scheduled every 4th day or more often, right? More often is fine, just not more infrequent. Then that gives you an instance, the same schedule works for the optimization problem and gives you that heat or better. Okay. All right. If you take a different threshold, right, instead of 80, take 100, you get somewhat higher numbers here. And the problem becomes easier to schedule. Now, if you try a heat lower than 80 in this small example, you see the numbers go smaller, obviously. But you see there's a problem in that A can never be scheduled, because this edge AB now has a frequency of 1. They have to meet every single day to not be unhappy if you want them to be less happy or less unhappy than 80. But there must also be at some point a schedule with C, so A can never be satisfied in this example. This means in this small example, there's an easy way to prove a lower bound, namely anything below 80 makes a locally impossible situation, which means 80 is the best possible solution. Okay, the optimal heat for this optimization problem is 80, because 80 had a schedule. Everything below 80 gets into an an impossible local situation, so you cannot have a schedule. Now, unfortunately, that's not the general case. So here, that's what I just said written up. Here, a very local argument was enough to prove that is not feasible, that this blue version was not feasible. And that turns out, in general, is not so easy. Given some decision version, this blue part, we don't know of a local criterion that would always tell you whether something is feasible or not. Yeah, I guess hardness is another dangerous word in this context. Computational hardness of the problem, though, here is actually simple to show. But we'll need a problem that I think we haven't seen before as a reduction partner. First of all, we can show that already a very simple special case is as a hard problem. Either you say in the optimization problem all the weights are the same, all the growth rates, or you say all the frequencies are the same thing. Now, it turns out that this is essentially equivalent to a problem called edge coloring, where you're given a graph and you have to normally when we think of coloring graphs, we color the vertices, and then a proper coloring is that no two vertices with an edge have the same color. Here we're coloring the edges instead, with the same rule. No edges that touch in an endpoint can have the same color. So maybe digression on the side. So it's kind of in a research talk, you would have just left it there. And if people know what edge coloring is, then great. If they don't know, then tough luck. Try to follow the talk either way, or try to puzzle it together from what's on the slide, or Google it while people are still talking. So I'm just recording this here because I think it's worth having that in mind. So it's an undirected graph. There's always vertices and edges. And formally, we want a function that colors the edges. And it has a certain number of colors. Also, mathematicians are really boring. When they talk about colors, they just mean numbers, right? And then I guess it's first apply this and then do the color by numbers. I guess as a decision problem, we're given the number C of colors that we can use. And let me be specific. So it's the numbers 1 up to C. So that we have C different colors. And now whenever we have an edge U, V, and VW in our edge set, they have to have different colors. UV. How well can you do in this problem? Like, let's, before we jump on, think a bit. Let me give you some basic, very simple graph. How many colors? Can I do it with 1? I guess not. Can I do it with 2? Seems easy. What if we add a few more edges? Like this? I cannot give it red or blue, I guess. So the first, maybe somewhat obvious observation. C is always going to be greater than capital delta, which is the largest degree in the graph. Because at every vertex, you have to color all its edges in a different color, right? So how large could C be in like a bad example of a graph? Let's see. A bad example could be a relatively complete graph. So maybe with 5, we can still see this. That's a K5. So we need 5 colors for sure. Can we do it with 5? Let me try this to be colored red. Then I might do this red. And aha. By symmetry, you see the same procedure is going to work for the other 4 edges. Right? Is it clear? So I'm taking one of the other, say we focus on this vertex, and I'm trying to color all its edges. I can always put one color here, and then the parallel edge in the way I've drawn it can get the same color. And that way I can hopefully get all edges colored. Maybe running out of distinguishable colors, but other than that, we can leave the last one black. So hold on, we need at least delta colors, and we could do it with delta colors. Is that always enough? That would be a boring problem. So can we find a graph where we need more than that? I think the smallest examples are already a bit annoying to find. For bipartite graphs is indeed true. Yep. But we need 3 colors. That's nice. Yeah, okay, that's a nice and small example, yeah. And it's not bipartite. So here it's delta plus 1 if you translate it to that. Okay. Now it turns out delta plus 1 is always enough. That's a non-trivial result. It will pop up on the slides as well, but it's called Wising's theorem.
Yeah.
Did we make a mistake? Oh, you're right. Haha. Yes, 5 vertices, but yeah, good spot. So it seems rather you usually need delta plus 1. You can do it with delta for bipartite graphs. I don't think that's obvious though. Wising's theorem says delta plus 1 is always enough if it's a simple graph.
I think for complete graph is always delta plus.
Yeah, I guess the same construction generalizes. But how to prove that? How to prove in general that delta is not enough? It's a bit harder. So it's an interesting problem in that if you were asking this as an optimization problem, what's the smallest number of colors? In this case, it's really the same as a decision problem because there's only 2 outcomes. There's only 2 possible values for all simple graphs. Graphs can either be of type 1 or of type 2. Nevertheless, the problem is NP hard.
I think we can try to prove by going by the vertices, like color each edge of the vertices like with delta, and then move to another vertex and move to another vertex, and in the complete graphs, like I didn't do the math, but it should be like by the time we can come to the half of the graph, it should be apparent that we need 1 more color.
That's the thing is, so trying to prove that you need delta plus 1 for the complete graph. The way you described it is kind of one algorithm fails. But why is there not some other solution? You would somehow have to show that every possible solution is bound to fail.
We're talking about delta plus 1 for complete graph.
Yeah.
Okay. Well, that's because one vertex has degree delta. So
Yep.
we need at least delta. And it's connected to all of the other vertices.
Yep.
Which have edges in between 2. Which no. That's a mistake.
It's a bit tricky. I would say it's a good puzzle to think about.
I think that was a good direction because one of
Sure.
the edges will already be colored.
Yeah, not sure if this is very simple short argument. Same for Wising's theorem is not super quick to explain, even though it's not super hard either. Interestingly, it's also kind of an algorithm. You can use this. The proof of the theorem gives you an algorithm to construct the coloring with delta plus 1 colors. But it doesn't guarantee that that's necessary, right? So it always constructs some coloring with delta plus 1 colors, but there could have been one with delta for your graph or not. Yeah, a piece of notation that pops up, chi1 of a graph is this number of colors. This was our C from earlier. And that's an NP-hard problem. Even when you restrict it to some specific graph classes, so even on relatively harmless graphs, this remains a hard problem. And that's what we'll use for the reduction, even though the reduction here is kind of boring. Sometimes it's called chromatic index because chromatic number is the number of colors you need to vertex color a graph. In case I've ever made snarky comments about graph theory and their inability to pick good names, that's another instance. I think. So if you have such an instance of this nature where it's essentially unweighted, all the weights are the same. If you have an edge coloring, like indicated here, then that induces a schedule for our polyscheduling problem. You just take the color classes. They have to form a matching because they can't have edges touch that have the same color. So then you just do a round-robin schedule through the color classes. And that gives you a heat, the number of different color classes, because everything grows with 1 per day. Okay. And you can also go the other way around. If you have some edge coloring, if you have some polyschedule, and you want to get an edge coloring back, any schedule has to schedule matchings. Now the schedule could be very long. It could use tons of different matchings. So you can't easily say, I'm going to take day 1 as one color, day 2 as another color, and so on until it cycles back. That might use many more colors. But you can cheat a bit, or you can play this trick that the color that an edge gets is the first day where it was scheduled. And you can show that that's good enough. Because again, the first day an edge is scheduled still has to form a matching. If you take all the edges that are scheduled the first time on a specific day, it still has to be a matching. And every edge needs to have a color because you have to schedule it at some point. So if you had a schedule of heat h, then every edge has to appear in the first h days. So you get at most h colors from this construction. Okay, so what do we learn from that? You know, the chromatic index in a graph. We discussed outside of the slides a bit. Wising's theorem says it's a most delta plus 1, and it has to be at least delta. There's more. I mentioned that the original theorem already has an algorithm, but it's not very efficient. And there's been a recent flurry of papers trying to make the algorithm for finding these colorings more and more efficient. That was just funny because it popped up days before the conference. There's further refinements now. So you can do it in It's not linear, but very low degree polynomial time. Fine for us. But if you want to find exactly whether it's delta or delta plus 1, it's an NP-hard problem, even for 3 regular graphs where all the vertices have degree exactly 3. Seems like a very well-behaved class of graphs, but still here is leaving the problem hard. So we immediately get from this 2 things. One is that the decision problem is NP-hard because you can reduce it to an NP-hard problem. That's what we've done on the previous slide. You can do a little more here, though, because you know it's even hard for these graphs with low degree. And that means if you could somehow build an algorithm that distinguishes in polyscheduling between, so if you had an algorithm that can approximate the polyscheduling problem very well, you could use that algorithm on these low degree instances to distinguish between delta and delta plus 1 colorings, or colorability. And specifically, you get the statement, you cannot have a 1 plus delta approximation unless P is NP for any delta less than 1/3. Just because such an approximation immediately tells you whether a 3 regular graph needs 3 or 4 colors, and so it would solve this NP-hard problem. So here, at least in the bonus part, you've seen some inapproximability result. It wasn't very exciting in that we didn't need any new theory. And there's lots of cool theory with probabilistically checkable proofs and all that. But that had to go. OK. You can also do a different thing. And this we pushed further in a different, in a follow-up paper. You can also embed the satisfiability problem directly in one huge polycule. That was Ben's core work there. Maybe at this point I can just say, if you use this reduction and you start with a bipartite graph, then as I mentioned on the handwriting, for bipartite graphs, you can strengthen Wising's theorem that you can always do it with delta colors. So on bipartite graphs, this problem of chromatic index becomes trivial, and this reduction doesn't give you anything. So if you take polyscheduling restricted to bipartite graphs, then this doesn't work, but you can generalize this satisfiability reduction. That still works. And so you can show even if you start with a bipartite graph with all the implications, then the problem is still hard. So we have a hard problem. What do we do if we can't solve it exactly? We could either randomize, or we could do FPT, or we could do approximations. And here I'm going to show you some approximation that I think is a cute idea. We have, from this hardness result, we have an algorithm if the thing is unweighted, that is not exact, but is also not far off. A delta plus 1 coloring is almost optimal. It's a delta plus 1 divided by delta approximation by just combining the upper lower bounds. And we even know there's some theoretically efficient algorithms for finding this delta plus 1 coloring. Let's ignore how they work for here. So we could use this if the instance is unweighted. So this only works if the growth rates are all the same. So if we just apply that without anything else, it doesn't help much, because you get this from the upper bound. You have that you can at some point you will have to have the maximal growth rate, or in the worst case, all you can get from this coloring is delta plus 1 times the largest growth rate. And the lower bound you get is delta times the minimal growth rate. That's how long that has to wait. But this ratio could be as big as you want. So here's all we know so far. The heat needs to reach delta times G min. because you will need different delta, different colors. So someone has to wait at least for delta days. But also any edge with a single growth rate, you can't do that every day. So it will, or even if you do it every day, it reaches Gmax. And the best we have so far is round robin of all the colors. So that alone is not super satisfactory. But how can we still rescue something from there? This round robin of the color classes works well if the graph is unweighted. Can we make it approximately unweighted? That's the idea of this layer cake of an algorithm. You split the graph into different layers where this is the entire graph is shown here with the light edges kind of deleted at that layer. This layer is, you have all the edges that have a weight or a growth rate between the largest possible and half of that. So everything in here has a growth rate that's within a factor of 2. That's approximately unweighted. And then the next layer is the same again, but just one layer shifted. So you have half the maximal up to a quarter of the maximal. And so you have that going on for a while. For how long, we'll have to determine afterwards. So within one layer, you know that you have a ratio that's bounded by 2. So you can use this round robin schedule within a specific layer, and you're only making a small error, namely a 2 times delta plus 1 over delta approximation. That's from this formula. If you put Gmax divided Gmin is 2. Now we also need, we can't simply do one layer, we have to do all the layers. So we could schedule all the layers round robin, which means every day we'll decide which layer is currently scheduled, and then within the layer we go one step through its round robin schedule. And if you do that, that means you're only making progress in the schedule of the layer once every L plus 1 steps if you have L layers. There's always there's L true layers, and then the last one that collects all the rest, all the edges that have lower growth rate than this one. That's why it's L plus 1 layers. And then you have to take the worst heat that you get from any of the layers. That's how much it's slowed down by the round robin of the layers, and that's how much you have as a heat within the layer if you were just doing the layer round robin. The color classes plus 1, and then that's the largest growth rate in that layer. Okay. You also get a lower bound from each layer because you have delta I in that layer times the lowest growth rate or the maximal growth rate. That's a lower bound for any individual layer, so it's also a lower bound for the entire instance. And so you can combine these two and somehow with that bound your approximation ratio. So specifically, you can distinguish where you get the maximum of the upper bound from. We don't know which one that is, but we can make a case distinction in the proof. One option is that one of the proper layers dominates. That means this upper bound is equal to this for some layer I. And there's also the lower bound for that layer is valid for the entire instance. So if you divide those two, then you get a 3L plus 1 approximation. Yeah, so we bound it here. The 3 comes from getting rid of the delta plus 1 over delta. And there's another factor 2. So there would be 3 halves at best, and there's another factor 2. That's where the 3 here comes from. The other option is that the lowest layer dominates. So this upper bound that we get for the heat is from the lowest layer. Then we need a different lower bound. So here we use the largest growth rate lower bound, and you get this approximation if you divide by them. So now we have 2 different cases, and we don't know which one occurs. So the best you can do in general as a kind of worst case guarantee is you equate the two so that in the worst case, you get the best of the two. Let me rephrase. You equate them so that if you don't know which happens, they make you suffer equally much. And from that, you can compute how many layers you should use. And in this case, it's a logarithmic number of layers, and you get a 3 log delta approximation. Okay. That's the point. You can think about how you would do this. And this is the point where we found different approaches. But let me show one thing there first. So one property that this layering algorithm has is that at every point in time, it schedules a matching. And well, every scheduling algorithm has to do that. If you take the matchings it schedules over time, they are disjoint. So if you take the schedule, the set of the matchings that you get, I'm taking the set of all those matchings. That's a disjoint collection of matchings. And you can show for basically if your input consists of let me start with this. Suppose this is your polycule that you start with. It's disconnected. There's a single couple that's always going to meet, I guess. And then there's here these constructions where you have one desirable guy in the middle or person in the middle that has to alternate through the different partners. If you want to do this with disjoint matchings, then it turns out something like a log n approximation is best possible. Because if you want to be disjoint, then you can put this one together with one edge here and here and here. But it means that this couple that was unrestricted otherwise and could have met every day is now only meeting every 4th day. And in general, you can't do better if you want disjoint matchings. If you want that, then maybe the next would be this and this and this. You can't make this also blue because it's already red. So you're always going to pay the heat here delta times whatever that heat is. Even though it's unnecessary, you could easily make a schedule that makes that one every day, this two alternate, the very natural thing you would do in this case. But if you insist on doing disjoint matchings, and the algorithm implicitly does that, so the algorithm is in a way best possible, but only under this restriction, which is not a very natural restriction if you look at the problem zoomed out. So what does this in general look like? The largest degree here at the end is essentially some square root n. If you keep going like this, how many vertices do you have? It's the sum of the first integers. And then the degree of the last star that you build is still polynomial in n. So after taking the logarithm, yeah, I didn't tell you what the weights are. So you have to put growth rate 1 here, 1 over 2, here 1 over 3, 1 over 4. So you'll get to 1 over root n or so. Oh, you stop early. The worst bound comes from stopping early, I think. Okay, let's slowly finish the story. So you can do better on the approximation. There's one curious thing that I want to show because it ties into another part that we talked about. That's this notion of density. And these pinwheels come from another problem that turns out to be a special case of this polyscheduling problem. That's the pinwheel scheduling problem. Since you're already familiar with the polyscheduling problem at this point, it's a single star. You have one person in the middle and then other partners that don't see anyone else. You can reframe it in this case because then the edges are essentially equivalent with the leaf vertex. You have different tasks and they have to be done with a certain frequency. Say, think of household chores. You have to do the dishes every third day or so. You have to wash the laundry every, I don't know, 14 days or 7, depends on how big your wardrobe is. What else? Maybe you have to clean the floor every, whatever. A bunch of tasks with some given frequencies, but because you're lazy, you only want to do a single thing a day at most. And so the question is, if you're given such tasks with certain frequencies, is it possible to schedule them so that you do it at most one thing every day and still all the tasks are done with the desired frequency? The problem is harmless in the formulation, but it sometimes needs really tricky solutions. And the first one where this happens is this instance, where you have some tasks that needs doing every 3 days, then 4, 5, and 8. And it's indeed doable with this kind of periodic schedule where you do the task 8 only once every 8 days exactly, and the red task every 4th day, but then the others are really a bit funky. The 5 is sometimes done much earlier, but that's necessary to squeeze in the 3s. And it's an instance, if you think about this harder, then you see that there's no nice solution where you have the tasks, you let the thing rot before until the last moment. If you just do it deadline driven, it wouldn't work. There's also an optimization version of this, which has been another fun paper. So it's for that conference was somehow well suited. Now, what is density? If you think about this frequency, if I give you 3 tasks and you have to do them, all of them have to be done every other day. It's not possible. There's just too many tasks. What's an easy criterion to decide when it's certainly not possible to do the tasks? I mean, the number of tasks itself is not the point because you can have very high frequencies. If I give you 5 tasks and they have to be done all every 100th day, then yeah, you just do them once in a while. So the computational complexity of this problem is a big, weird question because it's not known to be in NP. It's a very weird case. It's unclear if it's in NP, and NP hardness seems to be the case if you encode this is a question of how you specify the input. These are numbers. If you write them in binary, but one after the other, we don't know whether it's NP hard. If you allow to give a whole bunch of tasks, all with the same frequency by saying, now come 500 tasks of frequency 700, then it's NP hard for this more powerful encoding, where you can compactly represent a large number of tasks if they have the same frequency. Then it's NP hard. Again, for the general version, the more natural one would be just every task is written down as a binary number. But for that, we don't know. And so it's really like It feels like it should be a hard problem, and certainly with this restriction it is. But it's a bit awkward. It doesn't nicely fit the usual kind of reductions. And it's not in NP, maybe, because the output size is so big. Even okay, what's the output size? What's the output? One option is to say, give me the schedule if there is one. And the schedule could be very long. In particular, there's an instance with powers of 2. If you have a task of frequency 2, and the next 4, 8, 16, 32, then you can show these are feasible. There is a schedule, but the schedule is as long as the last frequency. So exponential in the number of bits you need to write this down. Now, of course, it's a decision problem. If I give you just the tasks and ask you, is there a schedule? Yes, no. You don't need to give me the schedule. You just have to prove to me that the answer is yes. But we don't know whether that is so for an NP problem, right? We want some short certificate for yes instances. And that's not known whether that exists. It seems the schedule itself certainly doesn't do it, because it can be very long. But for the concrete examples where the schedule is long, where the only schedules are long, it feels like you can easily compress the schedule by saying, yeah, I give you a short program that outputs the schedule if you need it. But whether that's true in general, we don't know. It's a weird problem. And of course, polyscheduling inherits some of that weirdness. It's a bit easier because of the graph. It's more natural to specify things explicitly. For the simple kind of, I'm not looking for an exact characterization. I'm just looking for a simple criterion that if I give you an instance and it has a certain property, then you can say, certainly not possible. And that's what density does. You essentially take the reciprocals of all the frequencies and sum that up. And the idea is, essentially, it's an LP relaxation. Now, we haven't talked about what the LP for this thing looks like, but the problem tells you can do one thing every day. If I tell you can do a volume of 1 every day, but you can split it between tasks, the problem becomes much easier. Then a task that needs doing every 2 days is done if you do it half every day. A task that needs doing every 7 days is done if you do it a 7th every day. And so if I give you tasks where this fractional demand every day sums up to more than 1, then you can't do it. Now, this is only one direction. The other direction is not immediately clear. And here's an example that shows you could have a density below 1. So fractionally, you could do it. But if you want an integral schedule, it's not possible. So here's an input 2, 3, and some large number. And if you try to schedule this, the 2 needs to be done every 2nd day. You could do it twice in a row, but that's never going to help. You're just wasting 1 day. And then the 3 has to go in between, right? There's no, if you have a 3 here, you could have done it here, but that's already blocked, so you have to do it earlier. So there's never a day left for doing this task M, no matter how big the frequency is. But the density of this thing works out to be 5/6 plus a little bit, 1/m. A half plus a third. And so for a long time, there was this conjecture that maybe this is indeed working in the other direction. So if the density is above 1, impossible. Density below 5/6, always possible. You can always find a schedule. And that turns out to be true. But it took 30 years to prove. But the final paper is actually very clean and nice. It's a bit embarrassing nobody found it earlier if you want. But it's a combination of some clever tricks. But it's a very nice paper to do some, I don't know, some seminar on or so. There's a few simple tricks, plus then here's a finite selection of cases. If I can prove all of these work, it works. And then that's done by computer exhaustive exploration. Now, if you look at this, and you say pinwheel scheduling is a special case of polyscheduling, maybe there's something like this density for our problem as well that tells you here's an instance. If I check this density and that's above a certain number, I'm sure I can give up. That's the last thing I want to show you. There's something like that. It's just a little less nice maybe, but the derivation is cool. As I mentioned before, you can think of it as a fractional solution. You do a fraction of a task every day. So in polyscheduling, that means for every possible matching of edges, I can say I can spend a fraction of every day on that matching. The difference already is there's a lot of matchings, whereas previously there was a small number of tasks. Now, if you do fractional solutions, like for pinwheel, is actually there's no need to distinguish days. Every day can look the same. But you do within the day, you schedule the different matchings. And so we can find this, the optimal such fractional solution with an LP. So this capital M is a set of all matchings. We try to minimize the heat. And what's the condition? Well, on every day we can do at most one volume of meetings. And what's the site condition to have that heat? We'll get to that. And then the fractional solution is between 0 and 1. And we're only looking at the maximal matchings, because you can always, if you schedule some matching that an edge could be added to, you can schedule that extra edge and you'll never be worse off. To be below this heat h bar, you have the growth rate, and then now what comes here is a bit awkward. What does it mean? How long does a couple have to wait before they meet again if we meet fractionally every day? So, but you can, the clean solution is to say if over the course of the day they met for a fraction of 1 over f, then it takes them f days until they've collected one meeting, and so that's the waiting time you should use. So this is 1 divided, summing up all the matchings where they are scheduled. And so in this whole fraction is, or the denominator is exactly the fraction of each day that this couple spends together. And then 1 over that is the waiting time until they've collected a full meeting. Now I promised you that this is a linear program, but there's variables below in the denominator. That's not a linear program. Okay, so it actually, you need to massage this a bit. But if you look at this constraint, the g's they look like variables, but they're constants. They're given from the input. These are the growth rates. So you can take reciprocals on this constraint. And now you have a 1 over L. That sounds bad. That's another variable in the denominator. And that's also here the objective function. But now we're just renaming our variable to 1 over L. Sorry, I did just the change in variables here. And now I'm doing the reciprocals. And then instead of minimizing 1 over L, I'm maximizing L. That's the same thing. So you can reformulate the problem as a linear program. You have to keep in mind that the objective function here is 1 over the actual heat. Okay, so what's that all for? This is an LP, so we can dualize it. And from the dual, we can try to get any feasible dual solution is a bound on the optimal value here. So it's an upper bound for L, so a lower bound for the heat that we can achieve. And that's what you get as the dual. Again, you could basically follow the rules, but you need to simplify the result a bit. You're minimizing some obscure number x, such that for every edge, a certain set. So you're kind of putting weights on the edges, and it has to cover 1. And there's this site constraint on x that for every matching, if you sum up this weird, these weights divided by the growth rate, that has to be at most x. I failed to find a very nice intuitive explanation for this. Maybe there is none. or it needs to be found. But you can still take this to define something that plays the role of density, which is essentially the best possible value for this x. And it comes just from these guys here. So we don't have a closed form here. It's not like a simple, for pinwheel scheduling was just take the frequencies, take the reciprocals, sum them all up. Here it's still, for every edge, you have to pick some variables. And any solution, any way to pick, to assign numbers to the edges, you get this unwieldy expression, and every choice gives you a lower bound. So it's a useful tool to prove certain lower bounds, but you need some creativity to still do it. But we've worked a bit further with this, and it turned out useful. Okay, at the time this was all we had. So it's a NP-hard problem. You can't approximate it arbitrarily well. And the best thing we had here was essentially a log n approximation. It's a bit like set cover. And for set cover, you can prove that log n is likely the best possible approximation. Again, the part that we had to cancel. But there's reduction style things. They're not exactly as strong as p equals n, not equals np in the assumptions, but not too far away from that. A bit like for randomization. And so there are problems where this log n seems the best possible. But we now know polyscheduling is not one of them. You can get a constant factor approximation for those. Not better than 4/3. I think the best proven is 5 point something as an approximation factor. So certainly we've made some progress there. This is no longer the best, but there's a big gap to the lower bound. And you can study the problem in many different ways, restrict it to certain things. Let me say one more thing about pinwheel scheduling, because there's another area of the module that we can kind of touch on with that problem. If you take in pinwheel scheduling the number of tasks as the parameter k, in the sense of a fixed parameter algorithm, the input size could be much bigger because some of the frequencies, these are numbers and you have to write them down, whereas the number of tasks could be smaller. Then you can prove that it's a fixed parameter tractable problem with respect to the number of tasks as parameter. I don't know if that's practically of much value, because usually the number of tasks is not small. Still brings together that other bit. So that's not what I wanted. Pinwheel scheduling problem with k tasks is FPT. That was a different paper, and maybe we're not going to get into it. Okay, let me leave it with that. Do you have questions? There's a lot of open problems that maybe I could list a few. If you have do you have questions? Go back to the slides maybe. Yeah.
What if the couples wanted to meet in groups?
Yeah. It's a natural kind of question, right?
Yeah. Then we would be. Yeah, I guess we should solve more creed coloring in that case.
Yeah, I think yes. So Ben thought about a name for the problem. I think that's as far as we got. And it's not so clear what to do there. Yeah, you're coloring cliques in a I mean, it's a hypergraph then.
Maybe, yeah.
But the problem is it's not exactly a hypergraph edge coloring, because if you have one edge, so you could have a subset. I don't even know what the proper definition there is. So the question is if if a triad, if 3 people meet, does that mean they've also met as couples? Does that tick their desire or not?
It should
Probably.
be, I guess, like, I don't know, like 3 people form a throuple, so they meet together. That's what I thought. And or like 5 people meet together.
But so say you have, you have the 3 people is one hyper edge, and then also a pair of them.
Desires each of them, and I guess we can take the average or the sum of the 3 desire.
My point is, I think slightly a different one. So I think Ben called this the safe pinwheel scheduling poly scheduling problem. If you have 3 people, then there could be one hyperedge representing they meet as a group of 3, but there could additionally be pair edges. Now, is it satisfying this couple edge if they meet as a group of 3? Yes or no? I think this is not so clear, right? Sometimes you're happy to meet in a larger group. Yeah, for sure. So you mean like ask people first what yeah, so as a abstract problem, if you say these are independent hyperedges, right? They meet separately from the meeting as the triple, then you could say it's hypergraph edge coloring, and it's probably not very different from what we've looked at. Apart that you don't have Wissing's theorem and all these things, so you'd need more math to work with it. The other version, I guess, is more natural, that you say, okay, these want to meet, these want to meet. Why don't they jointly meet and be married together? And then what even is the formalization there? I guess because they could still meet as a pair if this guy is somehow busy with someone else. So it makes sense to have that edge separately, but now the whole problem becomes much harder. Yeah, I think it's sensible to define, but it becomes much harder. Yeah, nothing's known. I mean, another, if you try to, obviously poly-scheduling was a fun motivation. The problem, the abstract problem, can be a bit more sensibly, sort of boringly applied to other scheduling tasks. If you think about other cases where it might make sense to have different people assigned to different tasks or things like that, or different, it could be groups of people, it could be personal trainers and their clients. They want to meet for training sessions and they can only meet one a day. Then often it makes sense to assume that there's a group of people that are essentially identical. So whether a client meets, okay, maybe with personal trainers it's not so interchangeable. Maybe these are more personalized relationships. If it's workers and tasks, the more classical scheduling, you would at least assume that the workers in the same group can all do the same tasks, and so it's is a bit less individualized. This actually makes the problem a bit harder if you translate it to this graph edge scheduling. If there's several edges that are equally fine to schedule. Yep. Mm.
Different amounts of time. So
Sure. Okay, if both is if both the time, I guess one is enough. You can scale it so that somehow the duration. But yeah, for pinwheel scheduling, you can certainly look at variants where you have maybe 2 people, right, and they jointly do things. And the tasks could also take a different amount of time. Then it gets a bit more nasty. But these variants have been studied, I think, as well.
I was also thinking about breaks where
yeah,
certain people might not want to meet like every other day. They might like
lower bounds. That's an interesting one. Yeah, so instead of just growth rates, you also have kind of repulsion rates or yeah. Should be easier to handle, right? You just skip a meeting or so. If you have the meeting slot and you decide, let's skip one, that sounds easier to do than not making the time.
Yes, but when you skip it, you have to put it somewhere. It's not going to disturb the other desire.
Something where they have to meet every 3 days, but don't want to meet every other day, then
yeah,
it gets complicated.
Yeah, if you have tight combinations of this, then it's not so easy. Then they want to meet exactly every 3rd day. Yeah. Yeah, there's a couple of variations on this, and for many of them, questions are open that are similar to this, or are even not clear for pinwheel scheduling either. Whenever you make the problems more rich, like adding different job processing times or other constraints, they don't tend to get easier. Yeah, so we're mostly out of time. If you want, I can try to sketch this update on what can be done for approximation. I don't think we can really do it in 10 minutes, but I can start with the pinwheel scheduling. So that we can probably do. So there was this bamboo garden trimming problem. BGT, bamboo garden trimming. So this is back to the pinwheel world. You just have different tasks, and I guess you remember the picture with the bamboo plots and this panda that was briefly on the slides. That's the idea there. So you have different bamboo plants, and they are known to be fast growing, right? So they grow a fixed amount every day, and you have this lazy gardener that can cut 1 bamboo a day, and when it cuts a bamboo, it cuts it down to 0. And the question is, what is the height of the garden that you need to reserve? So maybe there's some tall, fast-growing one, maybe slower ones. Every day, this little gardener can cut down 1 bamboo to 0. So you see, this is really like the growth rates for polyscheduling, same picture, but you're visiting exactly 1 pole every day, and you cut it down to 0. And the same kind of high water mark. What's the lowest high water mark that you can guarantee? That's the goal. So it's exactly polyscheduling on a star. On a graph like this, where you have these different growth rates. So you can do a 2 approximation for this algorithm, for this problem, with the following little trick. First of all, if you have a pinwheel scheduling instance, so the decision version with frequencies, where the density is less than 1/2, then you can always find a schedule. And that works as follows. So you're given these tasks with frequency A1 up to AK. And we know density means the sum of the reciprocals is less or equal 1/2. Now, if you think about how these 2 problems relate, remember that's what I shown in the example originally. If you have a certain height that you want to maintain, then you take the height divided by the growth rate, and you have to round up. Then you get essentially the frequency that you can tolerate. Okay? So height divided by growth rate, and then round it down. That should be your frequency. That was on one of the early slides. We can try to do this here. To get a 2 approximation. So what we need is a lower bound for what height we definitely need. And for the bamboo garden trimming problem, a lower bound is that this heat will always be at least the sum of the growth rates. Okay, I have AI, these are frequencies. Let's say this is G1, G2 for the growth rates. And the reason is obviously you can do just one task every day. So you have to let them every day. I guess the argument is it's easier the other way around. Suppose you could keep the height of the garden strictly below this total growth rate, then every day you would cut a bamboo that is less tall than the total growth rate. So you remove, in terms of the biomass that you take away, is less than the total growth rate. So every day the garden in total grows by that amount, and you cut something that's smaller than this amount, that can't work at infinity. Okay. I think that's the easiest way to explain this. A bit, yeah. There's no cutting of columns, but yeah, you cut rows. Okay, so bamboo garden trimming where you cut rows, another problem for another day. The total growth rate sounds like something you want to try as the height, but that's going to be the best you can possibly do. For a 2 approximation, we're going to try 2 times that. Yep. Okay. Then we should get the following decision instance for which we want to schedule. We take all the growth rates. And we take 2 times the, let's call this G, capital G, the sum. You take 2 times G, you divide it by the growth rate, and you round this down. That should be your frequency. For the ith task. And the claim is that if you do that, you end up with a solvable instance where you can find a schedule for it. And for this, we will use this lemma that we haven't proven yet. So let's calculate the density of this instance. Let's call this Fi. So it's 1 over these lovely terms. So I want to upper bound this by 1/2 to apply this. The rounding down is annoying. The rounding down means I'm dividing by something smaller. So the best I can do is say if I leave this off, then I'm dividing by something bigger. So I guess I have to subtract 1 to make that right. maybe this is not, the rounding at this stage is not convenient. The way the algorithm really works is to take these, but round them down to the nearest power of 2. So that would be one way to round. Let's see, if we take the lemma first, the way to solve pinwheel instances of this sort is we go from the AI to new density, where we take 2 to the log of AI rounded down. Or less or equal AI. So I'm taking all the AI, round them down to a power of 2. That means they're still at least AI over 2, right? And if I take the density of that, now because we started with a density of less than 1/2, that sums to at most 1. So there's still hope to solve this instance even if you round things down. But the key property is that there are powers of 2. And so if the density is at most 1, and it's more than one task, then the largest density can be, the largest frequency here, the smallest frequency will be can be a 2. And all of them are powers of 2, so that they never collide, so you can put them in slots modulo the largest. Say, and we don't have a name for those. The largest of those AI prime will be some power of 2. And so you can put the tasks in these slots. How can I show that this always works without writing down the full algorithm? If you have a 2, then you have at most, then you either have just 2, 2, or you have 2 and something else. You could put that 2 in the even slots and keep all the odd slots for the rest. But the rest has, again, density at most 1/2. So in a way, you can do an induction over the largest frequency. You can have at most all of them, that frequency. You can put them into slots. I don't know if I'm able to explain this in short time. Let's say the greedy algorithm works of generating a schedule. And that comes from the powers of 2. The magic of having density at most 1/2 is that you can round down to powers of 2 and you don't get above density 1. And now you have powers of 2, so the greedy algorithm works. And how to get the approximation algorithm for the bamboo garden trimming problem is to take this larger threshold and treat these as frequencies. And you show that they have density at most, at most density 1/2. So you can turn that into an approximation algorithm. But I think you have to do the rounding to powers of 2 and the rounding of frequencies to numbers in one step. Otherwise, it gets a bit questionable. So the intermediate instance I generate here would be without the rounding, and you would have to live with non-integral frequencies. Okay, 10 minutes was a bit ambitious for this. Maybe let's leave it at that. The best way to generalize this to polyscheduling may not have been found yet. So open problems. The complexity status of this pinwheel scheduling problem, as I mentioned. Is it NP hard? In the normal encoding. Polyscheduling approximation factors. We only know some range, and it's not clear what the best is possible. Then the generalizations, where we discussed what can you say about these? They're going to be at least as hard, whether they have constant factor approximations, I guess not so clear. And there are many sensible restrictions to problems where the graphs are from some set. I think these are also underexplored. Good. Had some fun? Let's briefly discuss what we do tomorrow. I suggest I put on Slido the normal Q&A, and you can fill in questions. I'll send this on CampusWire as well for the others. You can fill in some questions on Slido up till the session tomorrow. If there's not enough questions for us to make sense to meet, then maybe we'll skip it. The Q&A tomorrow, so like the last lecture slot is replaced by the Q&A. I sent this on CampusWire, but I didn't say it now. That's just an offer. If you want to discuss some questions about the entire module, we can do. If people feel they prefer other ways to do that, or they don't need it, that's fine. So if I don't see some questions on Slido, I suppose we call it off. If you want questions to discuss in the group, throw them in there and upvote other people's questions. Okay. Then maybe see you tomorrow, and see most of you Thursday or Tuesday, I guess. There's still a tutorial today to discuss the last sheet. Good point. Yes. See you later. All of you. Yeah. Forgot about that.